Hello everyone, it's April 15th, normal tax day. And if you're wondering why I'm hiding behind an acid and a base, it's because we're going to add fire to it today. So hopefully this will work. You know how my demonstrations have been going. So it's April 15th, we're going over 15.3. You're in Faith Christian's chemistry class. So, I'm dripping wax. So let me hold that back up and let's take a quick word to the Lord in prayer. And then I'll show you this demonstration and then we'll talk about why we're doing this. So Heavenly Father, please stay with us today and help us to keep us safe, keep us healthy, keep our families safe. And Father, we just pray that you'll grant the wisdom of heaven upon all the leaders of our country and our world and upon us too. Help us to learn more about you. Help us to learn more about chemistry and your creation. And always be with us. We love you in Jesus' name. Amen. So today is 15.3, it's our section on chemicals, acids and chemical reactions. This is something you all could do at home if you wish. I have a very easy base, which is sodium bicarbonate. I have a really easy acid, which is acetic acid, also known as vinegar and baking soda. Of course, what's going to happen when I pour this into this, because it's basically the volcano happening. What you might not know is that there's also a chemical reaction that's occurring, which means this reaction is creating another chemical that will have an effect on this flame. So let's get really close here. I am going to begin to pour this in. I did not blow. I did not blow out the candle, but as you could tell, the candle went out. Why did the candle go out? Because this reaction was not producing oxygen. This action was producing carbon dioxide, and it got to the point that there was so much carbon dioxide that the oxygen depleted to the point to where this flame could not burn, and it went out. And we'll continue, if you'll turn to page 254, we'll continue reading more about the acids in chemical reactions, and we'll continue with that. This was, of course, a bicarbonate. Try that at home if you wish. It's pretty fun. But I'm not going to go light my candle. I do not even have a lighter or a match. I had to use the Bunsen burner to light this candle. So let me set this to the side. Let me grab my book. I have made a complete mess here. I'm going to try to set that to where it will not turn. I'll try to set that over there too. And let's get started on your chemistry today. So I'm on page 254. Since it is in the presence of H3O plus ions, and that is common to all aqueous acids and accounts for similar properties, then all acids are going to undergo some of the same reactions. In this section, we will consider some of these reactions. So we have ionic and net ionic equations. When studying reactions in aqueous solutions, including most reactions involving acids, it's often useful to consider each ion separately. I'm going to turn you around here. Do you know why I'm turning you around? So I can sit down. I'm just unplugging my computer, which is not good because my computer does not have that good of a battery. So, well, now it's in a big knot. Just having a wonderful time. You know why? It's because I actually got a demonstration to work, and now I've just cursed the rest of the video. All right. What a mess. Now I have the cord over here. Well, we'll deal with it. So, if you continue reading, remember you do have some test questions in here, as well as your next quiz is over 15.3 and 15.4. I will go ahead and tell you that the majority of your quiz questions is going to come from 15.4. But we're covering 15.4 as well today. So that's because both of these sections are fairly short. So let's go on. So an equation written to show the predominant form of each substance present in the solution, ions or molecules, is called an ionic equation. In ionic equations, compounds that ionize or dissociate in solutions are written as ions, and undissociated compounds are written as molecules. Still cannot get my thing adjusted. I am not meant for YouTube stardom, because YouTube stardom, because I really do not like this. So I am not going to read specifically everything, but they basically, like most of your book, they use a lot of examples to keep explaining what an ionic equation is. So ionic equations have compounds that ionize or dissociate in solutions are written as ions, and undissociated compounds are written as molecules, and then they go through these different types of acids and bases that are in 15.4 and 15.5, as well as insoluble substances and weak acids. If you don't get it from 15.5, they refer you back to table 12.2 that's on page 202. Ions that appear in the same form on both sides of the ionic equation have not reacted. They're spectator ions. They're just there to see what's going on, and they may be completely canceled out of the equation. The result is a net ionic equation in which only the ions actually involved in the reaction appear. And they give you an example of how to get this net ionic equation. You guys are in high school, you're not going to have to worry about it. Maybe if you take college chemistry, you're going to have to get this to a little bit more. But I'm not going over that section. That's something that you just have to, you might want to go over. If we were doing homework, we'd do it, but we're not going to. Let's move on page 254, to reactions with bases. So bases, according to the Arrhenius concept, are substances that produce hydroxide or OH negative ions in an aqueous solution. And way back according to the table that you looked at on 15.5, which gave all of those relative strengths of acids and bases, and remember you have to memorize some of those. Hopefully you've got all of those written down, and you definitely wrote down silicic acid, because I can't find it anywhere, and it's on a chest. But according to table 15.5, that OH negative ion is a strong base, and then of course the ammonia ion is a strong acid, right? No, where did I get ammonia ion? What am I saying? The H3O plus ion is a strong acid. In that process, both properties disappear, which means they neutralize each other. So neutralization, it's any strong acid reacting with a strong base, basically ends up with a net ionic equation given in equation 15.16, which is like what you have right above where I read. Here comes a test question. So whenever an acid is neutralized by a base, a salt is formed. That's right at the bottom of 254. So right here at the bottom of 254, it is not bold at all, but that little word is a test question. When an acid is neutralized by a base, a salt is formed. In your test question, it kind of asks it in a different way. When a strong acid and a strong base react to neutralize each other, what happens? A salt is formed. That's so when a strong acid or a strong base react to neutralize each other, a salt is formed. When an acid is neutralized by a base, a salt is formed. Think you got that? So let's talk about salts. Most of the time when you think of salt, it's like past the salt, right? Which is sodium chloride, basic table salt. And we've used it in some of our experiments we've had so far. Most of the time that's all you think about. But we've also had an experiment where we burn lots of metallic salts. So there's thousands of salts. On table 15.6 on 255, they list all kinds of salts that you have there. So what is a salt? A salt is an ionic compound composed of any cation except H plus and any anion except OH negative. So as such, salts have no common features to identify them, as like an Arrhenius acid and base. However, from the perspective of an acid and a base, a salt might be may be considered as an ionic compound containing the cation of an aqueous base and the anion of an aqueous acid. So that's how they think of, a chemist would think of a salt. We've already dealt with a bunch of salts. Like I said earlier, we burned salt and we judged by its flame what type of salt it was, and we looked at their uses in preceding chapters. We didn't always say that they were salt, but being ionic compounds, all soluble salts, one way to know that it's a soluble salt, dissociate 100% into ions in an aqueous solution. And it once again refers you back to 12.2. That must have been 12.2 was the chapter that you all just finished up and took a test on. So those two chapters involved a whole bunch, if you remember. So neutralization is not limited to a strong acid or just a strong base. A reaction between a strong acid and a weak base, or a strong base and a weak acid, can also neutralize. That net ionic equation totally depends on the weak acid or the weak base. It wouldn't be the same for all reactions, of course. And then once again, they go over what to do. Like they have the potassium hydroxide as a strong base, along with hydrofluoric acid in water and what it combines. And then the neutralization used in a laboratory in the case of spillage of acid. So usually a weak base, such as sodium hydroxide or something like that, is used to neutralize a strong acid, and they show you that on 15.19. Coming back to basic chemistry, where the majority of us, we're not going to be in a chemical factory, even though I have two relatives. My sister actually works in a chemical factory. That's going to have to deal with this. But what do we want to know? How about heartburn or acid indigestion? That may be relieved, and what that does is it neutralizes the stomach acid, normally using a weak base. And that would consider, they gave you like three different, whether it's sodium bicarbonate or whether it's magnesium, and some different antacid preparations they show you there. As well as they give you most of the time, if you've got something like Alka-Seltzer or something that you throw it in some water and it starts to effervescence, then that's normally some sodium bicarbonate with some citric acid that's causing that effervescence. So you've got a picture of that right there. So reactions with bicarbonates and carbonates is what we started our class with. We used sodium bicarbonate, and then I just threw in some acetic acid, which is vinegar, and even though we've done that a lot in class, you saw that it ended up producing something that actually extinguished that candle, and that was the carbon dioxide that came out of it. So you saw that one. Another familiar acid reaction involves carbonate-containing minerals like calcite or dolomite, carbonate minerals found in various forms like limestone, marble. I think the one we did is we actually used the acetic acid with the calcium carbonate that was in eggshells. Remember doing that? Of course, I've got calcium carbonate, just little chips as well. Of course, a more familiar reaction is baking soda and its production of CO2 gas. Baking soda and vinegar, all the CO2 gas was coming out, and that's what ends up happening. Ingredients like buttermilk or sour milk contain an acid. So remember when we're talking about, lots of people think that milk is a base, and it's actually slightly acidic. So buttermilk and sour milk contain an acid which reacts with bicarbonate also to produce CO2, and that actually helps you with some, that baking soda is used in some, baking soda, baking powder is used in bread making. It makes a quick bread rise up quickly compared to a yeast that normally you have to sit it to the side and the yeast has to build and grow. That reaction is what causes it to grow, the reaction between the sodium bicarbonate and maybe the milk. So the following are some typical reactions between a carbonate or a bicarbonate, and they've given you both of those right there. You can continue to read that. One thing that I thought about setting up, but I didn't because it's pretty undramatic, is the figure that they gave you on 15.9 on page 256. And that's when you take hydrochloric acid and you stick either a zinc strip or a copper strip. We've actually done that before. We dissolved a little piece of zinc in hydrochloric acid earlier this year. And it took about a day or so, I think, but then the zinc, which we just put in a tiny little bit, completely reacted and was, it looked like it disappeared. Of course, matter is neither created nor destroyed, so it's in there. You've got kind of a zinky mixture with the acid. But one common laboratory method for the production of hydrogen gas is to react an acid like hydrochloric or sulfuric. Remember, those are two big acids used in industry. We learned that sulfuric acid is almost an indicator of economics because it's used in so many products. And it reacts with zinc, and then a salt is also produced, and they give you that chemical equation. Not all metals, though, react with acids, however. Metals may be arranged in order of their ability to react with an acid, and that's what the table you have on page 256 is, how reactive those metals are. It's considered the activity series. Metals below hydrogen in the activity series will not liberate hydrogen gas from acids. Metals above or more active than hydrogen in the series will react with acids in solutions to produce a salt and 2 molecules of hydrogen. Thus, copper will not react with aqueous hydrochloric acid, but zinc will. Though copper or any metal below in the series will not react with a non-oxidizing acid such as hydrochloric, it will react with an oxidizing acid like a nitric acid, but not to produce hydrogen. Instead, copper reacts with the hydronitric acid as this chemical equation shows you. So, and then they show you a couple of different oxidizing acids that are right there. So your quiz question, I don't think it was a quiz question. You have a test question from this whole section, and it's basically what happens when an acid is neutralized by a base, and that's when a salt is formed. The test question reads, what happens when a strong acid and a strong base react to neutralize each other, and you put down a salt is formed. We're going to continue on to 15.4 because pH is a really long section, so that will be one section by itself. So continue on down to 15.4, and that's equivalence and normality. And this is where you need to begin writing not just test questions, but also some quiz questions, because you do have a quiz on 15.4 and 15.5. I'm not real certain. I think I sent those home, but I'm going to make certain. If not, then you know it's coming the next week, or when you come back to school, you'll have it. So if we look at the equivalent masses, exactly 1 mole of sodium hydroxide will neutralize 1 mole of hydrogen chloride. However, 2 moles of the sodium hydroxide are needed to neutralize a mole of hydrogen sulfate. This is true because each mole of the hydrogen sulfate releases 2 protons when it dissociates, compared to the 1 proton, now I'm going to biology, 1 proton of hydrogen chloride. So hydrogen sulfate is diprotic, and hydrogen chloride is monoprotic. As a result, twice as much sodium hydroxide is required. Instead of dealing with mole amounts of acids and bases and neutralization reactions, it's often more convenient just to use amounts that are chemically equivalent. So 1 equivalent is the amount of the number of moles of an acid that will supply 1 mole of the protons, or the amount of the base that will supply 1 mole of hydroxide ions. You need to know what the equivalent mass is for a test. So that's your bold word that you have on page 257. Your first bold word is equivalent mass. So what's the definition of equivalent mass? The equivalent mass of an acid or a base is the mass per equivalent of that acid or base. It's very similar to molar mass, which is the mass per mole of substance. So the equivalent mass of an acid or base is the mass per equivalent of that acid or base, similar to the molar mass, which is the mass per mole of substance. Now, for hydrogen sulfate, since 1 mole supplies 2 moles of hydrogen plus, or H+, that ion, the equivalent mass is 49.04. And I'm going to let you read that on, because basically it's basically using with some chemical equations how they get what the equivalent mass is and showing you how a scientist or a chemist would use that. Where I want to go over is basically to go over to normality. So if you read on to the next section, it's normality. The concentration of solution may be expressed as molarity, which we had in the last we had chapter 12. Chapter 12 we had molarity, which is the number of moles per liter of solution. However, it's often convenient to express concentrations of solutions of acids and bases in the terms of equivalents, which we talked about earlier, instead. So since 1 equivalent of acid will react with 1 equivalent of the base. So the concentration of a solution expressed as the number of equivalents is normality. So you have to know that little formula there, but you're really not going to use that form of the formula. So you might just want to circle it and then go on down, because that's where I'm going to tell you where you have one on your quiz question. Since the number of equivalent solute and the number of moles solute are related by the number of equivalents per mole, molarity and normality are likewise related. Knowing the molarity or the normality of a solution allows us to find the other. What I want you to write down and concentrate, because this is what you have on your quiz, is, for example, monoprotic acids like hydrogen chloride, or the other one that we've got right here is basically molarity is equaling normality. And because of that, there is 1 equivalent per mole, or basically molarity is equaling normality. So for diprotic acids, since if it's like a monoprotic, it's basically 1 times molarity. If it's diprotic acids, it's 2 times the molarity. On your quiz, you have a triprotic acid. So look at how this comes down, because I can tell right now, I can feel confusion coming across the internet. So this is what you have to know on your quiz. You can look at normality to get it in your brain how that's used, but basically what this looks like is molarity equals normality. That's where it starts. For example, monoprotic acids equal normality, because there's 1 equivalent per mole. Now, if you've got diprotic acids, a diprotic acid, right? So we talked about the normality of a diprotic acid, where here it was just 1 mole, just 1, right? Diprotic is going to have 2, so it's going to be 2 times M, right? 2 times M. And let's just go. This is monoprotic. I'm probably being way too basic, but I want to make sure you get it in your head, because sometimes y'all call me on quizzes and you can't figure out stuff, and I tried to go over it in class. So diprotic would look like this. On your quiz, they were hoping you would get the assumption, then normality with this one would end up being that. Now, on your quiz, they will actually give you what the molarity is. You don't have to figure out what the molarity is. You simply have to know what the capital M is standing for, which is that big standing for the molarity. So make sure that you are able to complete that calculation on your quiz. So that has completed 15.3, 15.4. We have not exploded the classroom yet. That's one reason why I come to school to do my videos, because I could actually injure someone, as well as the bandwidth at my home is taken up by my children. So have a good day, and finish your tests and your quizzes as well as you can, and hopefully we'll see you soon, and stay well. Goodbye.